let's talk about spring forces. So first, I want to do a quick review of vector addition and subtraction, because it's a concept that's important to understand before we develop the spring force equation. So, say we have a vector A, and we're adding it to vector B. Well, then we can put the vectors tip to tail, A plus B, and that will give us our resultant C vector, C. And just a reminder, this is the tip of the vector, the endpoint, and this is the tail of the vector, the starting point. So if we want to subtract vectors, say we want to do A minus B, well, that is the same thing as doing A plus negative B. And remember, the negative of a vector is just pointing in the opposite direction, right? So B pointed in this direction, so negative B points in the opposite direction. And so when we can still do the same thing, the tip to tail thing, right? So A plus negative B will give us this vector D. And you'll notice that if we take positive B, and we put it tail to tail with vector A, right? Tail to tail with vector A. So this is B, this is A. Well, then A minus B points from the tip of B to the tip of A. And I have it written over here. This is the key concept. This right here is the key idea I want you to take away. That A minus B is the distance from the tip of B to the tip of A, provided that the two vectors are tail to tail. I'm going to say it one more time because it's important. A minus B is the vector that points from the end of B to the end of A, which is this vector D here. All right, I'm going to skip what's written down here because I just talked about it all, and we're going to go right into the spring force developing in the equation. So what I have here is an inertially fixed point O. I have the attachment point of the spring, denoted by A. And then I have this spring end, the end point of the spring, which I called P. The vector that locates point A is called RA, and it points from the inertially fixed point out to A. The vector that locates point P is R sub P, and that goes from the inertially fixed point out to point P. So you can see we have two vectors that are tail to tail, RA and RP. We just went over this, right? So the vector that points from the attachment point A to point P is R right here, and that would be equal to RP minus RA. That's RP minus RA, which is the distance from A to P, which is this vector right here, R. The magnitude of R is called L, which is just the length of the spring. That's the length of the spring. And then finally we have U sub S right here, U sub S, which is a unit vector that points from the attachment point to the free end of the spring. And that defines the directionality of the direction our force is going to be applied. And I think I'll have all this written down here. So L is RP minus RA. So going from the tip of A to the tip of P. Tip of A to the tip of RP. That is R. So L is just the magnitude of R, the length of R. That is L, length of the spring. The spring force acts along U sub S, which is the unit vector that points from A to P, right? We already defined the vector that points from A to P, which is R. So if we just divide R by the magnitude of R, that'll be a unit vector that points from A to P. So that's exactly what we do. R divided by the magnitude of R will give us a unit vector, U sub S, which is the exact same thing as this right here, right? So this would be a vector that points from A to P divided by the magnitude of the vector from A to P, which is this. Okay, I think we get it. We've defined u sub s. Spring constant. So the spring constant K, that tells us how much force is applied based on how much the spring has extended or compressed. Right, so if we have a positive displacement, then we're extending, and the force can be just read off the graph. Where K is really the slope of this line. If we were compressing the spring, then our displacement would be negative, so we would have a negative force. If we have a larger K, if our spring constant is larger, then our line would look something like this for a linear spring. So we need less displacement to produce a high force. And then if we have a smaller K, a very low spring constant, then the slope is going to be very shallow. And we need a lot more displacement to produce, higher force. All right, so here's the actual spring force equation. Spring force, which I call, it's a vector, F sub s is equal to negative, don't forget the negative K L minus L naught in the u sub s direction, where L naught is the unstretched spring length, right? So if the spring is sitting at L naught, there is no force on the system from the spring. So let's talk about the two scenarios we can have. We can either have the spring being stretched or extended, or we can either be compressing the spring. So let's first talk about extension. So if this is our initial configuration, this is when the spring isn't producing any force on the system, so it's just sitting at L naught. This is our L naught distance. If we displace this mass over, then we're extending the spring. So our L is now here, and L naught is still there. That's our unstretched length. And you can see that if we do L minus L naught, it's going to be a positive number, right? Because L is greater than L naught. U sub s just points off to the right. It's pointing from the attachment point, which is here, to the free end, which is there. So that's U sub s. And we would end up with something like this. F sub s equals negative K L minus L naught U sub s. And you can see it's in the negative U sub s direction is where the force is going to be pointing. So the restoring force is going to be in that direction, to the left, right? Which makes sense. I mean, just think about your own experience with a spring. If you extend a spring, it wants to pull your hands back together. So the force is going in that direction. All right, now let's talk about compression. Same idea. This is the initial configuration, L naught. And if we compress the spring, then L is now smaller than L naught, which means that L minus L naught is going to be negative. U sub s is in the same direction. But if L minus L naught is negative, we can take that negative out of the parentheses, and you can see it cancels that negative that used to be in front of the K, right? This was for extension. We had a negative here. But now that L minus L naught's negative, now it's positive. So the spring force is K, L minus L naught, U sub s. So now the force points in the positive U sub s direction. It's pointing to the right, where before, with extension, it pointed to the left, right? So that's how the sign is resolved in the spring force. He has to deal with the sign of this L minus L naught term. In a lot of physics textbooks, or even if you just Google spring force, like go do it now, go Google what is the formula for a spring force. It's going to be some variation of F equals negative K delta X, and that'll be it. That's all it'll say. And that's kind of right? That's correct for like a one-dimensional problem, but when we're dealing with 2 dimensions or 3 dimensions, you need a directionality component to the force. What direction is the force pointing in, right? And that's not present in negative K delta X. What this is missing is U sub S, right? So now we have a directionality component to it. So just something to keep in mind. And the last thing I want to talk about is this curvilinear spring, which sometimes you'll see. So if you have your attachment point here on this track, and the spring follows, the track, so it's curving around some trajectory, then the spring force is the exact same equation, except now U sub S is replaced with E sub T, which if you go back to our intrinsic coordinates, you'll know that is the the tangent unit vector. And the force is always going to be either in the positive or negative e sub t direction, because that is where the spring is attached to, and that is the only direction the force can be applied. It can only be applied either this way or this way, depending on if you're compressing or extending the spring. If you bring P out to here, then you're extending the spring. If you bring P back to here, then you're compressing the spring. Right? The spring force isn't going to act from this direction or this direction or this direction or that direction. It can only be tangent to the track, is how that force can be applied. And that's the end of the video. Okay, so the next one we'll do some examples with a spring to get comfortable using the new equation we learned. All right, see you in that video.